like I don't mind, like if you want to wait at 5, like whatever. It's a natural flow here.
I think we can. Okay, so thank you everybody for being here. It's a pleasure to have Lena visiting from Northwestern. She's an assistant professor there. She got her PhD at Caltech, then moved as a postdoc to IAS and then the Black Hole Initiative. And she has done a lot of work on a lot of very different subjects. She has string theory papers, she has planet papers, she has star formation papers, but a lot of her work is focused in the Galactic Center, so we'll hear a lot about that today. And yeah, so take it away. Thank you for being here.
Thank you so much, Alan. Exactly in space. Well, thank you so much for inviting. It's a great pleasure to be here. It's my first time in Toronto. Yeah, first time in CITA. Actually, that's my second time in Toronto, the first time in CITA. So today, we'll be talking about the black holes and the black holes, galactic center black hole. I will focus on a particular, our own Sagittarius A star. I'd like to give kind of broad overview why should we care about the black holes and why do we study their creation and other things. So black holes are direct consequence of the general relativity. And Einstein published general relativity in 1915, and few months after, Schwarzschild had Schwarzschild solution, which is a vacuum solution of Einstein equation. And while few months seems very quick, I also want to point out that it was few months while Schwarzschild was at the war in the trenches of the First World War. So it would have taken like a week in other conditions. So in 1939, it was actually established that black hole can be connected to collapsing stars, because that wasn't something obvious. When we right now think about black holes, which seems like, oh, that's just natural thing, you make the point small and it must be a mass collapsing there. But it took, as you see, about 25 years to get to this point. This was due to Oppenheimer. And in early 1960s, the term black hole was coined, and unfortunately not for any good reason, but because of the notorious Calcutta prison, which was called the Black Hole of Calcutta. And John Wheeler, who is usually attributed to creating the term black hole, actually picked it up a little later for its brevity in advertising value. And so it's stuck since then. So why do we care about black holes? Well, first of all, because black holes are just cool, they're kind of mind-bending, because the space itself hides something from you, and it is very alien to our natural perception of the world. So we want to study things like this because we are physicists, astrophysicists, astronomers. But black holes are also super important because they are actually shaping the universe. And what I mean by this is that black hole is a big potential well. And big potential well tends to accumulate stuff around it. So it's pretty much not a big surprise that every large enough galaxy has a black hole at the center, because large enough galaxy also accumulation of things. And when you have a lot of stuff sitting in a potential well, and it creates friction, stuff, getting heated, it radiates, keep falling down, and a little bit of energy liberated close to the black hole can send this like radiation pressure pulls kind of out, and you can liberate tons of materials on the outer edges because it's kind of loosely bound there. So the black holes are creating this powerful jets, they're creating powerful outflows. They are, being in the centers of all the galaxies, they are the ones ionizing the universe, of giving a big contribution to general ionization of the universe by blowing stuff around, they're spreading elements through the universe. So technically, while we study black holes, we not only do the cool stuff because they just cool and have these little beautiful throats which we like drawing. It's also because black holes are literally shaping the universe, and we want to understand how the universe works. And the particular accretion of black holes is very important because you need to power the engines, and they're powered by eating stuff which falls into them. So black holes are all around the universe, and it's no surprise that our own galaxy has one at the very center. This one has a particular place from a point of view that there will be no other black hole which environment we can study with such a high precision. It's a black hole for which we can see small clouds, we see individual stars, many individual stars, many small clouds, streams, and everything. So for other black holes, which might also be pretty big on the sky, etc., there is, for example, M87, which is about the same size as Sagittarius, but it's also 1,000 times further away. So we actually, while we can study its environment, we can never achieve such details of the Sagittarius star. So, because black holes are important to study the universe, and we have one in our backyard, it would be really advisable to try to learn as much from our backyard black hole as possible. One can say that, unfortunately, that's not any of these powerful big black holes which we can see in the distant universe. So it's not a quasar, which is probably lucky for us because we're here to discuss it. It's not a quasar. It doesn't have an impressive jet. It's even questionable whether it has a jet at all. But the thing is, these black holes is in this typical state, which underfed black hole, in which most black hole of the universe spend most of their time. They do have this outburst by launching jets and making great outflow, but they usually followed by the period of being reasonable quietness. So we have a typical accretion, black hole of a typical accretion flow in our backyard. Oh, by the way, if you have questions, please stop me in the middle. It is so much easier to answer questions when you know which slide they're about. Okay, sorry. So, yes.
Since you mentioned it, you recently mentioned like every large enough galaxy should have a black hole at the center. Like, how do you define large enough?
In this case, it's large enough, which is larger than the large Magellanic Cloud.
Okay.
If they're smaller, then no. Large enough is just too large, as they don't hold good on slides. So how does accretion of the black hole proceed? So we usually have this picture of accretion of the black hole. We have like a bunch of stuff accumulates, stuff collides with itself, different pieces. It's radiates something. It also settles on something which looks like a thin disk. Here's your interstellar black hole there. Here's the most common picture you get for the search of a black hole, except the HT picture. And technically speaking, that's not much difference from this picture, which is the Saturn rings, which is also Saturn rings are an accretion disk. It's a thin accretion disk which also rains into the Saturn. This, however, only works when you have amount of materials accreting into the black hole. You have abundant amount of material accreting into the black hole. What I mean by that is that you want stuff when it's accumulates around black hole, interact with itself, and create friction, radiate. You want your electrons and your protons meeting each other often enough so the protons, which get most of the energy from falling in the potential well, can pass it to the electrons, because electrons, as like a particle, doing most of the radiation. So they definitely cannot decouple from each other because they're differently charged. But if protons do not interact much with electrons, the electrons remain cooler and so just do not radiate. So you need this interaction. So you have dense enough material so for your disk to settle on something thin. However, you can be in a situation, and the Sagittarius is in the situation, where the amount of material around your black hole is not enough, meaning your protons and electrons would love to meet each other, it just doesn't happen very often. And the stuff falls toward the black hole faster than proton passes this information as energy out to electrons, and electrons do not have enough time to radiate. So your accretion flow remains hot, and so it doesn't manage to collapse into anything thin, and remain this, kind of hard to call as a disk. It's just a huge thing with a black hole there, which is this huge open area. Which is like, this is my artistic impression of the big funnel. It's not to scale, because it's very hard to show. This would just go up. That's it. Black hole physics involve a lot of problems, like electrons, protons, that stuff have different temperatures. You can have metallicity. You have, you have GR. You have, Newtonian gravity. You have different turbulence and lots of things. So those problems are complex enough to completely be not tractable if you try to solve it on a racing grid. It's just not possible. You can try to play some little games, but it's not going to be realistic in any application. So we do need simulations to study black holes. And naturally, there's something trivial here. So if you want to do a simulation, you need to know put as much physics as you can. You need a source of supply of a gas. And you need some input from observation which would inspire you how exactly to put your gas into the black hole. And so I know that many of you are doing black holes, but I think majority of you are doing neutron stars and other things. So I hope that not boring everybody with what part knows much better than me, and I feel embarrassed.
No, I think it's
Okay, I'll go through this quickly.
I think it's good. I think not too many people are doing black holes here, actually. Okay, it's not just black holes we're talking about.
Okay. So, supply, physics, and some observational inspirations. So we have a black hole, and as a supply of material, if we think logically what's the most natural thing to think about, we would say, well, we see this accretion disk and things, we see them everywhere, and Saturn, we see them in the universe. The galaxy itself is kind of big, roundy thingy which is orbiting. So we can probably supply the gas by putting some torus of material around. We're not going to care. It's like the torus will be important, but it's only from the point of view of supplying the gas. So then we'll let this system leave. In our simulation, we'll set the torus up, we'll put the black hole, we'll let it leave, and the gas will start falling into the black hole. And we'll be looking at some radius pretty close to the black hole, smaller than the tori. And that's going to be our experiment boat, because the whole job of the tori is just supply the stuff. Sounds very reasonable. How we set up the tori is a separate question. I believe the biggest tori so far is about 50,000 Schwarzschild radii, right? In simulations which are not nested. And typically it's about 1,000 Schwarzschild radii. And this is a particular type of the distribution of magnetic flux inside the tori. I've just put it here to show that this is quite a complex distribution, because the idea is this complex distribution give you something which you consider more nice and more physical close to the black hole. And then you take some observations. In this case, it doesn't matter where this X-ray image is from. We can say that majority of the gas which is put into black holes, like very, very close to it, must be very hot. It's just because it's very close to the black hole, lots of things going on, so stuff must be hot. And so we take inspiration from the usually X-ray images, which tells us some information about conditions of the gas. And so we tweak the parameter of the tori, etc., to make sure that our simulations close to the black hole kind of make sense. And you run this, you get beautiful images. This is a part image. This is some pretty typical images. This particular one from HT, but many ray tracing code produces similar things. And obviously, the tori model is a reasonable model, because when we were discussing it, we didn't make any crazy assumptions. But in general, things like this, while it's a model, it remains a model and has limitation. And for example, let us try to apply this model to our own galactic center. So it turns out that if you take an inspiration from this Chandra map of the galactic center, that Sagittarius is there, you can run the simulation, you can produce some images, but the problem you're going to have is that you'll have a variability crisis, that all of your models seem to not really match the simulations, no matter how well you try to tweak your tori situation. So let us see if the tori assumption in this case is reasonable, and maybe we can see by eye where it fails. And to do so, we're going to take like a broad look at the galactic center and build it step by step, including we'll come back to this image on the scale. And we'll see how the galactic center actually look like, and what we can do to describe it better. So this is the artistic impression of Milky Way's galaxy. The sun is somewhere there, somewhere about 8 kiloparsecs away is the center of the galaxy. You can also notice that it's closer by about 0.2 parsecs to UC, to Los Angeles than to Germany. But it's approximately 8 kiloparsecs anyway. So galactic center is mostly the most majestic on the sky. This is when it's seen from the southern hemisphere. Then, if you zoom in and go to constellation of Sagittarius, and that's why it's called Sagittarius, and it's covered with thick dust clouds. And you can see this region is very, very crowded. And if you zoom in, you pierce through the clouds and zoom in a little further, you'll see the structure, which is called mini spiral. And just on the side of it, you will see a bright dot, which is Sagittarius A star, and A asterisk stands there for the star because just A was already taken. Now, how do we know it's a black hole? So there's been Nobel Prize level work when the stars were tracked, and you'll see the passage of S2 stars, closest known star to the galactic center. And this is observations. So what we know is that star passes so close, and the object is so massive because it bends the trajectory of the star so much that it can be nothing but a black hole. That's how we know it's a black hole. Yes?
What's like the time on how fast that star is orbiting? Do we see observations of it moving around the black hole? Is it like?
So let me see. It doesn't. Oh, it has dates. The date ran in 2017. It's moving 18.
I think the orbital period of the whole thing is like 16 years.
Yeah, something like this, 16 point. So the best measurements of the mass of the black hole can be done when the passage is the closest. That's why the best estimations were from 2019. That's in 2018 the star passed. So next time it will come back in 18 years from then, which is 36, right? Sorry, 34. I mean, it was like last time by 3 months. So who knows? So let me now build you the galactic center structure by structure. So that's our observational coordinates, array and deck. You see west and east and flipped directions. That's just deal with it. At the center, we have a black
You
hole.
look at the sky, that's how it looks.
Yes, it's like you take it's like, oh. Yeah, that just makes perfect sense.
That makes sense.
So you have a black hole at the center. So everything here is to scale. Some lines which are supposed to be thicker are drawn theta, but otherwise everything is to scale. So we have a black hole. This is a circle around this is 1 parsec, and there is a nuclear star cluster which is densest around 1 parsec that extends further, like to 5 parsecs, whatever you want to stop considering the cluster. So this is the plane of the galaxy, and the galaxy rotates, and it rotates toward you, and then goes into the board right there. So this little arrow is like arrows pointing away, pointing toward you, and the little crosses points away from you. So this is a mini spiral, which I showed you a little movie of. Those are 3 streams of gas carrying material probably to Sagittarius, because it's kind of looking like this. So this arm is, if I'm Sagittarius, it's go behind the board and comes here. This arm comes away, comes in front of me and goes away. And this arm is unknown. It's, we might not see any rotation, or it's a part of the bigger structure, so there is no indication which side it rotates on. So this is, I'd like to also point out that mini spiral contains the gas at the temperatures of about 10 to the 4 Kelvin, 100, 10 to the 4 Kelvin, something like this. So it's a nice gas. So this is the round thing, it's circle nuclear disk. And again, it rotates, it comes here, goes like this, and goes away. So this is part is behind, this part is in front. So this one called circumnuclear disk or molecular ring, meaning the gas stays pretty cold, like 10 Kelvin, 100 Kelvin. I mean, it goes to like 500 Kelvin or something like this, but it's pretty cold and there are lots of molecules in there. So this is the clockwise solar system that contains most of the Wolf-Rayet stars, also with rotation markers at about 4 seconds. This is an old remnant of the jet, and some people believe in jets or not, but it does look kind of obvious on X-ray picture because it's line. So now this little circle right above the star is the Bondi radius. The Bondi radius is a radius where thermal energy of the gas, mv squared by 2, is no longer enough to fight the gravity of the black hole. So everything inside this radii is kind of heading toward the black hole. I see that it's spherical and things like this. So we're going to zoom in onto the Bondi radii and see what happens inside the Bondi radii. So this is our S cluster, which is surprisingly almost exactly the Bondi radii. The S cluster is the group of the stars which are closest to the black holes, and those are particularly well tracked because those are, you can see them moving like on month-to-month basis. You can see some other stars moving from year-to-year basis, which makes certain calibrations and different decisions as well. So this is S2 star or SO2 star. It depends if you close it to Germany and to UCLA. You can see where to close it. So this is the size of the orbit, and when I showed you was like a little tiny bit right here next to the planet itself. And to give you an idea how crazy dense this region is, this is to scale distance to our neighboring star. So from us to our neighboring star, we have about 1.34 parsecs, and it's put on to scale to this region. So within the same distance, there is a cluster of million stars. There is all these huge structures orbiting there. There is different types of clusters. There is different disks. Like this is a very dense region. It's seriously dense region. So let's abstract. Let's remember a little bit what we talked about in our accretion, how we considered mostly the X-ray observations, etc. So, Astor community, which was doing that sort of observation, had no doubt whatsoever that there are collision of clouds, there are streams, and so cold gas from these structures and from outside rains in the galactic center. Moreover, this structure itself, the circumnuclear disk, is actually in the process of collapsing into the galactic center. It's collapsing right now. It's not supported, it's just going in. So there is actually no lack of supply from the point of view of, bigger view of the galactic center, of cool gas to the galactic center. So remember the 50,000 short radio disk? It would be approximately here if the models were correct. And so we can see that we actually don't see any structure like this living there. There is a big cluster there, but there is no huge supply to the galactic center or something which is like connected directly here and feeding it. So its picture is not exactly what we like to simulate. And if I again zoom even closer, so this is the Bondi radius. So this is the biggest tora, and the typical tora is here, this little thing right here in the corner. But then, we clearly don't see any big tora in this radius, etc. But there is another issue here, is that our knowledge, which we took inspiration from X-ray observations, is actually right here, at 10 to the 5 Schwarzschild radius. So the Bondi accretion rate coming from X-ray observation gives us information on 10 to the 5 Schwarzschild radius, and it cannot give us information that is anywhere closer for the following reason. So here is an X-ray map of the galactic center, and this is the Bondi radius, which is almost identical to Chandra's resolution. This is a Chandra observation. Meaning there is fundamentally cannot probe anything which is smaller scale than 10 to the 5 from X-ray observations. And first of all, there is a huge distance from 10 to the 5 to 50,000, and even 2,000 is a more distance, because that's sort of things we have to approximate and assume that we know the power laws, and we understand that if we know something here, we definitely can describe something on that side that holds. But there is a thing I also wanted to show you. So this is an X-ray map. An X-ray map is of the same region I just showed you. Except there is nothing on the X-ray map you can see from this enormous structures you see otherwise. Circumnuclear disk, mini spiral. You can kind of see the jet. That's the only thing you can do. So the reason is that X-ray observations, they predominantly see the very, very hot gas at 10 to the 7 Kelvin. And they do not see the gas at the colder temperatures. But there is not a lack of that cold gas, and so perhaps it would be important to figure out how exactly we feed black holes when we take care, hot gas and cold gas and all together and see how they interact and move it over the black hole. And so it is an important question, how much does a contribution from the cold gas, here under cold or cool, I mean anything which is cooler than 10 to the 7 Kelvin, and sun is 10 to the 4, so cool here is still temperature of the sun. But for this region, it's pretty cool. So I will speak a little bit about how do you go about finding the cold gas in the galactic center and what you do with it. Any questions? Have I lost everybody already? No? Yes, one. I lost Bart. Sorry.
First slide already. No, the X-ray jet that you pointed out there, this stream, like it is generally accepted.
No.
This is a
Nothing on the X-ray, which is called jet, is generally accepted.
right.
So there would be one person who would say, you see I'm blinking it, you see there is a straight line there. I was like, come on, this is clearly a jet because it's a straight line. It's about parsec size. So it's clearly a jet. And then you showed another person, they're just like, oh, you know how many straight lines I can show you in this situation. Whatever. Yeah, absolutely don't trust it. So I was speaking to Mark Morris, and Mark Morris like, this is the robust jet. There's all the others, they're little, who cares, but this is a robust. And I showed the dial, and I was like, whatever.
So there is also no matching other radiation from the same kind of line? Or there is?
No. So that's the whole map. I don't think you can get much better than this.
No, I mean in other wavelengths.
Oh, other wavelengths. No, there is nothing robust there. So you see some feature and you say, well, that must be. No. Otherwise, we would have had any robust statements from the community saying that the jet used to be here, used to be there. There are claims of the jet, but I don't know, there's 20 of them, they all point in different directions. They have different sizes, and we see the signatures of activity, but
How confident are you that there's a jet at all?
I'm not confident, I'm just drawing it because it's very easy to show when I blink this picture. You can see that I'm not fooling you around, and it's exactly the same size. That's the only reason I'm showing it. It's on this picture just for this reason. No, I'm not confident at all, and I'm not doing X-ray observations. So when an X-ray observer tells me, the dial tells me I don't believe it, I like dial, so I trust dial. That's all the level of trust here. Yes?
How can we heat gas up to 10 to 7 Kelvin?
Yeah, so there's a bunch of these Wolf-Rayet stars, they have really powerful winds, and just by, they supply a bunch of gas there, and the wind speeds are like 1,000 kilometers a second, so just like, that energy, if you convert it all into heat, is like 10 to the 7, 10 to the 8 Kelvin. So if they collide at all, or even collide with like the rest of the material provided by the other winds, then it just heats up naturally. So so most of all this, the diffuse gas within this region is expected to be provided by those Wolf-Rayet stars.
Yeah, I'll actually show you X-ray thing. Oh, yes.
What's the basis for the other lines we have, the circumnuclear disk and stuff? What's the?
Oh,
You mean observationally?
You can clearly see them observationally. I can scroll in, like, yeah, they're there in the combination line and other lines.
Okay.
They are just, they big, yeah, it's a good point. I should have had a picture, which I did. But like if you know, even if you Google something like circumnuclear disk galactic center, you would see the whole structure lighted up on this particular molecule. Or like mini spiral, you will see mini spiral lighting up. So yeah, you can see that. bright material. There is no doubt about it. All right, how do you go about detecting cool gas which is close to the black hole? So when we observe X-rays, we have this very low resolution observations, about 1 arc second. But while we're still on the ground, we have ground observatories which can do much better than this. For example, IMA can give you 0.01 arc second resolution, which is 100 times better than X-rays. Yes, 100 times better than X-rays. And if you believe that there is a potentially some cooler gases close to the black hole, you can try to actually look for them. And you can, how do you go about looking for something like this you're really unsure about? You can use a combination line of hydrogen. First, because you know hydrogen probably there. When it is helium, the line is still the same. So you know hydrogen is there. You know that it's not dependent on metallicity, so you don't have to make a correction because you don't really know what sort of metallicity is in the galactic center. And also, when I started this project, I was a theorist, but you can't just go to an observer and say, observe something you want. You're being sent very far. And so that just happens. Turns out if you apply for telescope time, sometimes you can get it. And so I did this project, and this is ongoing for many years, but I'll show you a little part of it. So you go observe in submillimeter recombination lines. Oh, the reason you do submillimeter recombination line is because the dust between you and galactic center. And submillimeter just goes through the dust, and the gas is not there. So you can actually see through the dust. Otherwise, other lines you have to correct. And so the idea was to set the limit on the amount of cold gas in the region, because clearly it should be there. But turns out it was actually there. And there was a pretty clear detection. So that is round thing at the center is Sagittarius A star. It's just there for measurement. You see blue shifted on one side, red shifted on the other side. That would be profile, etc. So the interpretation was that there is a cold gas. It's a black hole. That's S2 star for the scale, and some cold gas clouds orbiting around it. And they are clearly going to die when they go closer to the black hole. But at these distances, which is about like 10 to the 4-ish Schwarzschild, they're still there. And on the picture of the accretion, it will put us, so this is a pointy, this is circle is a pointy, but the cold accretion of the cool gas is going to be about 10 to the minus 7 at about 10 to the 4 Schwarzschild, which is, if you look at those numbers, which is 10 to the minus 6 and 10 to the 5, and about 10 to the minus 7, minus 8 close to the black hole, puts you that somewhere in this region, and there's the whole row is empty. And I don't buy it. You can actually don't suffer and just come here. So it's about the same same contribution from cold accretion. Hot accretion, something happens here, and then they both feed obviously only hot stuff. So on the picture of the galactic center, this cold gas was somewhere here. It's also with rotation markers. And while it is about the same size of the tori, the set up tori is actually made of very, very hot gas, not of anything like this. So I do believe that majority of the simulations back then didn't have any cooling at all. Because why would they? It doesn't cool. There's not, the cold gas is not relevant at all in situations. But turns out it was there. And so while I was thinking, like trying to convince people that the cold gas is important, Sean was also thinking of how to make simulations of the galactic center more realistic, approaching from a different end, not a different end, like some different part, is that clearly we don't see the tori, but what we do see, we see the Wolf-Rayet stars, which are blowing winds, and so the work was originally started by Jorge Cuadra, like 20 years ago. Sean did the first MHD thing with magnetic fields and everything. And so, I'm sorry, but Calderon has the best image of that. How it exactly works. I keep thinking if you should make one at some point. So how does it work is that you start with an empty box, and the dots you cannot probably see here because of the how great the screen is, but there are white dots which are the stars. At some point the stars start blowing winds, and with time they fill the box, and it's kind of equilibrates into something more realistic rather than numerical artifact, and then you can study this, accretion behavior. And so I also believe the original plan was to see if you can reproduce X-ray observations. So like if I take the square from Chandra, blur it, get you here, and this will be simulated image, which is on average, make perfect sense, but it doesn't have any morphological structure of the real image. But on average, it's not wildly different. And so I spoke with Sean, I spoke with, actually I did speak to Jorge Cuadra, yes. And so Jorge Cuadra and his group, which is Calderon 19 and now Balakrishnan 2014, it had the Hydra goat, and in their simulation they do, if they roll it long enough, they do see accumulation of the colder structure close to the black holes, close to the black hole, and Sean doesn't. So we decided to combine our efforts and try something else. So together with Sid Khan, who is now at the University of Maryland, we originally wanted to keep Sean stars and add some mini spiral, these free streams of the gas. But then we got a suggestion that this mini spiral was probably originating from this disk anyway. And so you should start from the disk and see how it evolves. So we put the disk in there, and like nothing else, actually I'm wrong, we put the cluster there, but only for the gravitational purposes. And what this finally turned out that we did reproduce the colder structure was starting forming, because it turns out if you keep dumping cold gas, it tends to accumulate. And it's you get the fighting between cold gas being evaporated, but hot gas, getting cooler. But you get the structures which are starting accumulating pretty close to the black hole. But also, I thought it was quite interesting that we did see pieces of the circumnuclear disk being teared out and falling in, and some of them would be stretching. And we still need to write this paper, but the sizes of those clumps, if they're too small, they're pretty shredded by the winds. If they're too big, they form the disk, but if they are in a particular range of masses, they create extended arms. And if you multiply those very narrow range by a factor of 3, you get the mass of the spiral. So the winds are really something which is like dominating the region quite a lot. Well, so far I've been, those are the pictures. So this started with the winds from the circumnuclear disk, let it blow. And you can see that there is some ripple structure started accumulating in the center. It's like you zoom in and you see the pieces going in, being thrown out. And you can see the small structure being formed inside. It's, order of magnitude-ish correct size, but on the order of magnitude. Actually, a factor of 2, but the property is not exactly the same. But still, it accumulates there. So, Now you might say, okay, fine, great, it's pretty pictures, who cares? I mean, technically, who cares, they're pretty pictures. So what we also tried to do, we did not try to run variability on the accreting with the cold gas, various reasons, one of which is not clear when it is actually more realistic than 1,000 years in the past, 1,000 years in the future. But what we did, we tried to put Sean simulations into the into the Greece code, right? And we did the variability structure because when I started talking about, I mentioned that one of the big issues we have with applied Tori models to the accretion, initial condition of the Tori, and all of the resulting output, it's just too variable and it's not fitting. There are thousands of those models, but none of them are fitting. So we try to see if the wind model, which is more realistic thing, which is kind of not, you just have to kind of step back, look at the religions in general and think how to improve it. So we try to run the simulations on that and see variability. And so what we got, this is just a quick thing to remind you that Sagittarius star is a variable source. Not only it varies on the scale of years, those averages are just averages of observation taken during that year. So it's just keep walking around. But the variable on the scale of, this is 30 minutes. So within an hour, it can go up, down, and it just keeps continuously walking. It's visible. Changes are visible on the scales of seconds. A few seconds you can see that it changes to go down, up, down.
I was just going to ask why there are the jumps, discontinuities.
Oh, because observations are not conducted continuously. While it is a galactic center, probably most studied black hole we ever had. Observation is still done a couple of hours today, if you're lucky, maybe a few hours in a week, and then next year maybe you'll have something else. I tried to plot them such a way that the earliest beginning coincide with the earliest observation, the end coincide with the oldest observation, and it's just average because sometimes it's just 1 point, sometimes it's a light curve, sometimes whatever you get. But within those stretches, it changes on a scale of, as you can see, minutes and seconds. And so we did this experiment. So the upper part is not the whole data. It's not the whole data, absolutely not. It's just a piece of it. So for visual purposes, there are, I don't know, thousands of minutes. No, I'm wrong. Thousands of hours probably of observations is going. But those kind of gives you an idea what sort of variability you're looking. And so we saw that the same Torah simulation look like approximately like this. So you see a lot of jiggle. The math Torah simulation also gives you quite a lot of jiggle.
Why does the scale go up?
Huh?
Why does the scale go up?
It's a random thing.
Like, does it also go down?
Yeah.
Yeah, it's just
So it's just a piece of data with about that length. We just take some piece which was done as in the slow line, fast line, and I don't like when you see these pictures when they're compressed and you just see some peaks and you have no idea what's going on within the peaks. If you stretch them, the data goes. I forgot the units. But it's about definitely more than 100 times more than what is quoted here. 35,000 by 20, whatever. Oh, that's a summary. It's a lot. It's just happened to be that age and whatever it was executed. Okay, that was here. So no reason whatsoever, it just happened. So this one went up, this one is more or less jumping, and this one. You can see that the Sean's winds are much smoother. and kind of have a similar-ish wiggly structure as the observations.
Is this resolution independent? Like if you did shot simulation, double the resolution, would the line be equally smooth?
I think so, but you have to do it.
I think for Sane and Matt, it's also resolution independent, so it would make sense. We could do
Yeah, because I think if anything, like, because these are roughly the same resolution, and the fact that you don't see these small scale wiggles already in the Matt simulation, or in the wind simulation at this point, and I think the variability is dominated by just I would say the changing initial conditions, but technically the initial conditions are fixed, but like the radial dependence of everything in the initial conditions that's determined by the winds.
So because of his winds that falling in, and like his wind, that's with this slice of the accretion flow. You see, I think what we wrote in the explanation is that if you have tori is already on orbit. And so the stars start falling in that for something, instability develops, it has orbits to develop. Well, here it's just like, and it's already there. So it doesn't have time to develop, and so it's kind of look much smoother as a result.
Did you do, I don't remember, did you also do it for the Bondi? No. We went to. But yeah, so Chris was doing a lot of the ray tracing, and so now we've kind of lost that train.
We still have to write a lot of papers.
But I do hypothesize that like Bondi would be similar.
Yeah, Lena's argument is good. Right on that, then it should be.
All right, and I'm almost on time, and I'm going to, so the quantification of variability is, you plot something which is called structure function, which is you have a light curve, you take it one spot, another spot, subtract them, the average across the whole light curve. So pretty much the physical meaning is that if I give you a point, then you're interested in what's the difference in the flux going to be at tau, ahead or behind. It's going to be on average this value. And so structure function is kind of finicky to discuss because they're not that obvious. But the point is this one is the worst one. So it's the same tori. You see the circles is the observational data. Everything which was available, archival data, I compiled this. And you can see that simulations, same tori follows the observational curve and then departs very early at about 100 seconds, 200 seconds. It just departs with a different slope. If it has a different slope, it has different modes which are driving this, which are living inside the system. So somewhat similar, but here it falls pretty far. It starts departing at about 10 to the 3, but then it departs very abruptly. And the short simulations are clearly linear. Follow it, especially the blue one. And somewhere here we start losing, in the last few points, we start losing statistics. So we're getting statistics at 10 independent measurements, but 10, 100 is better than 10. So they start being wiggly here because we don't have much statistics. So it just follows it. And so this maybe silly conclusion to say is that if you take care of physics, turns out physics takes care of you. So if you don't put on physical assumption and you do your best with physical assumptions, whatever comes out is representing the true system you see on the sky a little bit better than otherwise. And I'll quickly say what's next. So my postdoc, Mark Gorski, who is at the CIERA fellow at Northwestern. It does not look as impressive, especially here, but it's a draft of the highest ever resolution observation imaging of the galactic center. Usually you see a little circle here, which is the beam, but the beam is smaller than a pixel, so you can't see it. And it's a little bit, it's a bit faint because all of the flux, which is otherwise spread over the big beams, is collapsed where they're actually coming from, and those bright points are stars, which you clearly see moving from year to year, which is super fun. So what we want to do, we want to create it's about 150 hours through ALMA archive collected and then cleaned and everything. So Mark is the genius of imaging. So we want to be able to see as deep as possible. We want to see outflows if they're there. We want to see smaller structure. We want to see how the accretion works in this region. And nothing, like no X-ray, nothing else can give you any comparable resolution to that. And oh, by the way, the Sagittarius is removed. That's why you don't see it. It's supposed to be here. So it doesn't terminate the map, so you need to remove it, so there is no artifact. It's right now. I have a student, Nicole Wiener, who, together with Alexander, they're working on extractive variability of the black hole because we want to see, want to understand it better. And the funny thing about variability, I think it's not getting as much attention as it deserves for the reasons that pictures is pretty, but pictures integration of everything. You keep spatial information, but you lose any time information. Especially on an object like this, you need to integrate for a long time. Variability, you lose spatial information, that's true. But you keep time information up to, on time scale, 2 seconds. That's very deep stuff. You can try to learn from it. And sorry, just give me a few thoughts. And so the best methods before would produce, there's like random data set. The best methods before would produce you something like this. And so they made it work. So it is incredibly thin. So it's very, very high precision extraction, which has never been done before. It's like Greece, complicated. We should try to wrap up that down. And because it's next time is my thank you slide, and then I'll go to the question. And well, as I already said, please take a step back, look at the bigger picture, and take care of physics so it can take care of you. And that's thank you.
It's really convincing, right, the variability of the light curve. I'm saying the variability of the light curve of the wind-fed model looks very convincing. But if you look at, so EHT has other spatial scales, right, not just ALMA, and you can look at the variability across.
Well, EHT's variability comes from ALMA because ALMA dominates the sensitivity.
Right, that's the light curve variability, but you can look at variability across other spatial scales.
Like variability of what spatial scale?
Of let's say closure quantities or just other.
Oh, other quantities.
Yeah.
So yeah, it's possible.
Because I'm wondering if the picture remains as convincing when you look at the variability of other scales, other spatial scales.
The majority of variability is coming from Sagittarius itself. It's a point source, right?
Sure. I'm just saying if you take
on the scales of, as far as ALMA is concerned, it's point source, yeah.
Right, but if you look at the interferometric quantities, now you're probing higher frequency than just the light curve, and so you can look at the variability of
yeah, yeah, it's possible. The idea was to calibrate this as possible, as precise as possible. More questions, concerns, disagreements?
What did you do to tighten up the air bars on that last part?
So
You said it was more sophisticated, but how? What was that?
it's getting more sophisticated every week. So first, you force the, so in this particular case, you know that so one of the problems in Sagittarius case is that it is the brightest source in the field. Usually when you do observation, you go to calibrator, which is brighter than the source. You calibrate it, and then you return to your, and observe, your calibrator. So Sagittarius is by far, by a factor of 2, the strongest source in the field, so you cannot, so you are self-calibration on your own source. Self-calibration is great, but by default, the serious source is constant. So you get the mass coming out of there. So what they do is they force the array into a phase center. So by force, like most of the emission is from there. So then they play with gain tables. They pretty much they hacked IOS calibration pipeline. And on every step, like I will go calculate gain table, you grab the gain table and you know before you apply it, and you do math with the gain table, you apply there. You also need to clean a lot of funny things. For example, interferometers observe like this, like your source, and it goes source, phase calibrated, source, phase calibrated, source, phase calibrated, source, and bus, source, phase calibrated. It's